Okay, so hi everybody. So I am Bruno Douine from Green Lab in Lorraine. So I'm glad to present to you my presentation about superconducting machines for aircraft applications. So the contents of my presentation, I will present the context of the electric aircraft, and especially superconducting electric aircraft. And secondly, I will present HTS motors for aircraft. It's not an exhaustive list of projects, but a certain list of projects. So first, the context of this project of HTS motor is the transition of aircraft transportation. You know that there is a Clean Sky program to reduce the CO2 emission. For this, we need, for example, more electrical aircraft or totally electrical aircraft. You see at the bottom some project on this from Kilowatt at the right side, like flying taxi, like solar impulse, or flying taxi Airbus, and so on and so on, 2 megawatts, like EasyJet 2022 or N3X NASA motors and generator. So what is the purpose of these projects is to have a progression to the electrical power requirement in the aircraft. I have this slide from Airbus. From the beginning of the 80s, the power requirements was around kilowatts, and for the future aircraft, it will be more than 10,000 kilowatts. So what is the objectives of the HTS motor for aircraft? First, for aircraft, we need to decrease the weight very high, and this is why we can, if we decrease the weight, you increase the specific power, and the target for this, for this specific power for the future, is to have a motor from 10 kilowatts by kilo to 40 kilowatts by kilo. For example, for permanent motor, we can say we can reach at the maximum value 10 kilowatts by kilo. That is more 1 kilowatt to 5 kilowatt per kilo for permanent magnet motor. We need also safety. For this, we need the robustness of the motor in an aircraft, and something like redundancy. For example, is it better to have just 2 motors or 10 motors or 20 motors? For example, for a big aircraft, is it better to have a 100 kilowatts motor, the 100 kilowatt motors, or just 2 1 megawatt motors? So there is some possibility of HTS motors for aircraft. So I present there some different architectures. For example, you can have HTS coils for DC part, DC current part, like inductor, or AC current part, or both. For example, I have here some coils from Green in a big motor for German Electric in France, or Superox coil for their project in aircraft. This is the first choice, DC or AC or both. You can use also HTS bulbs for HTS magnets or HTS magnetic shields. I will present to you that some guys in Japan, Professor Izumi, for example, want to use HTS bulb for magnet, to make magnet, but in Green, we prefer to use HTS bulb to make HTS magnetic shields. First of all, I will present the project of my colleague from MIE, Nikolai Ivanov and Konstantin Kovalev. It's a fully HTS machine for aircraft application. So you have seen this motor just before me. So I don't want to use a lot of minutes to present this. I just want to say that the positive points of this, it's because it's a fully HTS motor, it's tested and on load, and it works. But for me, the negative points is you have AC losses in liquid nitrogen. So if you have losses in liquid nitrogen, so on flying, you will need a big tank of liquid nitrogen. So it's not so good in an aircraft. If you decrease the temperature, you can have less cryogenic liquid, but it's a little bit more difficult to, for example, to cool down this kind of motor with liquid hydrogen, for example. A second possibility is to have HTS coil, but only on AC part with AC current. For example, one of the projects you have seen before, it's the SuperOx motor in a plane. So it's a 50 kilowatts HTS motor, and it was being tested on flying. So it's very impressive. It was made with HTS coil made by SuperOx themselves with AC current. But at the inductor, you have only permanent magnets, so you cannot have a very high magnetic field in the inductor parts. The positive points of this kind of motor, of this project, is that they prove that they can put on board this kind of motor and make flying tests. The negative points for me, it's also as previously, it's AC losses in liquid nitrogen. So they need in the aircraft a big tank of liquid nitrogen. So for me, to improve this kind of motor, you have to decrease the temperature and use, for example, liquid hydrogen. So you can also use HTS bulk. First of all, use it as HTS magnet. So Professor Izumi presented before some beautiful projects. So I just put a photo of a whole project of this team. So you can have also some project. It was a project in Cambridge University made by Professor Combs in Cambridge. Made with magnetizing coil, magnetized HTS bulk. So positive point of this kind of motor, you can have high magnetic field but very compact. For example, few Teslas, for example, permanent magnets. The negative part of this is you have to magnetize ex situ or in situ, and in both cases is very complicated for me. Also, another problem of this kind of motor, you have the problem of demagnetization of the bulk during the operation. So in the Green Lab, so we analyzed all this project and all the quality of bulbs and coil and tapes, and we prefer to make another kind of motor. It's the name is HTS Flux Modulation motors. So this kind of motor was invented by Green Lab during the 90s. And the first guys who work on this kind of motor was Philippe Masson. He's now in USA. So now we have a team of three partners. We have Green Lab with Thierry Lubin and Jean Lévesque, mainly these two guys, plus a team of Safran, with mainly Raymond Derget, Sabrina Hayat, and Rémi Biojo. and a team of cryogenic system. It's an absolute system with some guys like Jean-Marie Gaillard, Adrien Cipriani, Julien Tanchon, and Jérôme Lacapère on this kind of motor. So the basics of this kind of motor, we use HTS coil, but only with DC current. So we don't have the problem of AC losses in HTS coil. We use HTS bulks not as permanent magnets, but we use it as magnetic shields. And we use not HTS coil at EC part, but we use only copper coils for the moment. So, and this armature of copper coils is cooled down by air or by oil, for example. And to cool down the HTS coil and HTS bulk, we use helium gas circulation. So the positive points of this kind of motor, you have no loss at low temperature, no loss at liquid or helium gas temperature. You have high magnetic flux modulation. It's more than plus minus 5 Tesla, for example, we can reach. You can have the possibility to make multiple machines. So we can multiply this kind of machine. If you multiply by 2 the machine, you have just to multiply the length by 2. The negative part and the tricky part is that we have rotating HTS bulk. This kind of bulk has to be cooled at low temperature, so it's not so easy. So I cannot say a lot of words on this because it's on patent. So some photos of the first prototype. So you have to know that with Safran and Absolute System, we made one prototype, 50 kilowatts prototype at 500 RPM. You can see on this photo the rotor with the 5 HTS bulks on the rotor part. You can see also the 5 HTS bulks inside the HTS coil. And so the HTS coil is static and the HTS bulks are rotating. And you have also the copper winding, donc static, who produce the rotating fields. So the next step of the team of the consortium is to make a motor of 500 kilowatts for the same size, the same diameter, and the same length. For this, you can for example replace the BISCO coil by a YBCU coil. You can change the shape of the HTS bulk and so on and so on. You can also decrease the temperature operation. So we can increase the powerful by 10 just to changing the parameters. The Green Lab is also in another projects. I can see the Ascent Script project. This Ascent Script project, the leader of this project is Airbus. And in this consortium, you have also Safran, you have Green, and Absolute System. The goal of this project is to have a complete HTS system with cable, power electronics in cryogenic temperature, and liquid hydrogen, motor, and so on and so on. Another project who are a partner of this is IMOTEP. IMOTEP is a European project, investigation and maturation of technologies for hybrid electric propulsion. So it's the goal of this project is to see the potential of hybrid electric propulsion. And a part of this project, one of the work package is on the superheating motor. The partners of this IMOTEP, you have a lot of partners, 20 or more than 20 partners is Airbus, Safran, Green, the team of Mean in Strathclyde, KIT, MAEI in Moscow, and so on and so on. And now the conclusion of my presentation, you can see that there is several HTS motor for aircraft projects in a lot of countries all over the world. You can also, I can say also that the HTS coil and bulk cost is decreasing. So you can now make a coil with different kind of tapes, visco tapes, YBCO tapes, and so on. The issue of AC losses at low temperature is a big issue because you can see, as the previous presentation, you have a lot of AC losses in liquid nitrogen or liquid hydrogen. So it's a very, very complicated issue. But the last but not least, the motor weight is not only due to the HTS material, tapes, bulk, and so on, but it's more due to mechanical structure, cryocooler, cryocooling liquid, and so on and so on. So it's important to work with different partners to make a good superheating motor for aircraft application. Thank you for your attention.
Yes, so the microphone is better.
Okay.
Thank you. You mentioned for magnetized HTS machine that we can it can succeed some demagnetization that reduce the performances. Do you think that, on the contrary, when you use HTS bulk for screen, you can have some magnetization effect that you can reduce also the performances of your machine?
So the magnetization of the HTS shield depends on the temperature. If you have a very low temperature, the penetration of the magnetic field is very, very small. So you cannot have a very high magnetization of the bulk. So it depends on the temperature. So you have to decrease the temperature as far as you have no penetration or very small penetration. This is one of the advantages of the HTS field in comparison with magnets.
If I may reformulate, you mean that you should have some demagnetization, but it would be less than for magnetized bulk, maybe because they are in a less, when the bulk is magnetized, the magnetic fields and the electrical field is might be more sensitive to variation than when it's almost a zero magnetic field for the screen bulk.
If I compare, if you have permanent, if you want to make HTS magnets, you cannot have very small temperature because you need very, very high magnetization field, very high peak of magnetization.
Understood.
So you have to be at not low temperature, very low temperature. But for the screen, for the shielding effect, you have to be lower temperature because you have no problem of magnetization. You don't need a very high peak of magnetization. You understand what I mean?
Yeah, perfect. There is one question now in the room.
Hi, Professor. Thank you very, very much for your marvelous, beautiful, and very knowledgeable presentation. Now, I would like to know if it is possible to give some figures on what kind of cooling power is necessary per kilowatt for the machine. Electrical
The machine of this one?
Yes, anyone. I mean, does it change when kilowatts getting higher?
Sorry, I don't have this kind of information. It depends on the temperature, it depends on the loss, and so on. So
I may answer, Bruno, for at least for the one we have in our lab. So the typical cooling power is about tens of watts at 30 K. So this is the cryogenic cooling temperature, but this means you have a lot of kilowatts at room temperature. So at the moment, for the scale we develop, there is a huge factor between the cooling power and the electrical power you may consume.
And there is no AC losses, just DC.
Yeah, this is just the losses due to the radiation and so on, not the AC losses.
Thank you very much.
One in the chat, so I will read it. So Bruno, since the modulation motor uses concentrated windings for copper armature windings, is it so that the harmonics of the spatial magnetic flux are large? Is there any effect on the rotational characteristics? I'll let you read the question.
Yeah, I read the question, but it's not so easy to answer this. There is spatial magnetic flux harmonics. There is harmonics, but is there any effect on the characteristics of rotational characteristic? So I don't have the answer really, but because
it's related. We are working on the fundamental. So is the spatial variation of the bulk may change in a way? I mean, for example, the shape may change the fundamental amplitude, for example, if I can reformulate the question.
Fundamental.
If you change the bulk size, for example, if you use trapezoidal instead of you can change the harmonics fundamental.
Okay. We can change the harmonic fundamental to by changing the shape of the bulks. So Rémi Dorje with Safran is working on this problem. So you can reduce the harmonics.
So using the same shape as the coil, using trapezoidal bulk.
Trapezoidal bulks.
Thank you, Professor Douine, again for your presentation.